Okay, so there was this, you did this example in your homework. I want to kind of expand on this example and ask more questions about this example today in lecture. Okay, so we have g of y equals ln of y. So this is different than what you're accustomed to, right? So we're very comfortable, familiar with letting x be the independent variable. Okay? But it should not be difficult at all to transfer and to say, okay, y is the independent variable. So if I wanted to graph g for y values from 1 to 4, how will I do that? How am I going to graph the function g for y values from 1 to 4? So in this case, I want this independent variable, I want it to be on the vertical axis, right? So that we still are thinking y and x. So how can I graph? So what is g of y then? What coordinate is g of y? Yeah. But so how will I graph values of g of y will be what coordinate? X, right? We're going to turn the tables here. So my independent variable is going to be on the vertical axis. We'll still call it y, though. And then my dependent quantities will be x. So how will I graph g for y values from 1 to 4? So this is going to be interactive. Like I'm going to keep asking questions, and you should, in your notes, you should be trying to write it down before I reveal it, or I'm going to ask you guys for the answers. So a volunteer first here. What should I type in to graph x as a function of y? Yeah. Okay, and then if I want them just for 1 to 4? One less than or equal to y? 4. What do you think? Yep, this is it. Okay, so this graphs this function. Again, we're thinking about how y is independent. So we're going to start here. We're going to pick a value, say 1.5 or 2, and then according to g, the corresponding value of the dependent variable will be graphed as the x-coordinate. Right? So here's a point, say 1.12 and 3.07. Here's x. So here's the ordered pair. 1.12, comma, 3.0, I guess round to 8. So tell the person next to you what's the meaning of this point. Tell the person next to you, what's the meaning of this point? 1.12, 3.08. That's the x and y coordinate. Go.
So when 3.08, when y is equal to 0, then your function
Okay, so I heard Kenny give a very good explanation, so take it away.
So when your y value is 3.08,
Uh-huh.
then your x value will be 1.12.
Right, so now it's reversed, right? You're independent. We choose y first. We say when y is 3.08, 1.12 is the corresponding x coordinate, and where does the 1.12 come from? What is it? What's the meaning of that number? It's the function value, which is natural log of 3.08, right? So it's the value of the dependent variable, or the function value, when the input is 3.08. Okay, does it make sense? So it's like in reverse now. You got to think in reverse. Y is independent. You choose y, and then the function tells you the corresponding x. That's the way we're graphing this. Okay, so there we graph that. Okay, next. Define the arc length function for g in terms of y. All right, so I want to define the arc length function with the independent variable staying with y. Go, everyone work on it. Okay. Okay. Yeah, so okay, 2 pi ln of y times okay. Okay. All right, let's see. Agree with that. Riddick, you agree with that?
I think it is the surface area.
Okay. So yeah, so this is surface area. Okay. That's right.
Yeah, so you put 2 pi in.
Okay, so we don't want that. Okay.
And then change the y to t.
Okay, we need t's. Okay.
And then dt.
dt. Okay, here's our latest. Tell me your name again. Maddie. What do you think? How are we now? Agree with that? Yeah. So what does 1 to 4 give us? What does it mean, a definite integral? This will give a particular arc length, right? What do we want? We want the function for all arc lengths where y starts at 1 and goes up to 4. So what should I do? Okay, so we do a. So yeah, we could do our a to y, right? How about now? Okay, and we want to call that arc length is little s, and I'm going to do sub g for the function g, right? So this arc length function is computing arc length for this function, right? So we're writing a new function that computes the arc length for this existing function. So sg of a comma y. How about now? Let's see. I think I have that one already written in. Let's see how it compares. Is it the same? Very good. Okay, questions on that? So that's a little review there. Okay, now I want to graph. So let's look at that. There's the function. Here's my next task. I'm going to graph the arc length function in a new pane. So I'll talk about how you can open up a second window pane, but just get the function right first. I'm going to graph this arc length function so that the independent variable is on the horizontal axis and arc length is on the vertical axis. So we really got to think about this. Okay, we got to think closely about this. I want to create a new graph that's the graph of that function, right? It's going to tell me arc length for any given value of y. But I want to put the independent variable now on the horizontal axis when I graph it. And then the vertical axis is going to show me values of arc length. Okay, so see if you can figure that out. So again, we've got this function that's a function of y. And I want to tell GC to graph that function with my independent variable on the horizontal axis and arc length on the vertical axis. See, take a couple minutes to see if you can figure that out. Work with those around you. Think about that. This is a little tricky. What did you think? Okay, so she wants to do y equals, so let's be exact here. So y equals, what did you say? So that will, y equals g of x is going to graph the g function. Is that what we want? So what do we want? We want to graph what? Y equals arc length, right? So that's s sub g. Now the question is, of what? So this is, what is it? What are we telling GC? We're saying put values of arc length on the y-axis. Is that what we wanted? Right? Take values of arc length, the independent or the output of the arc length function, and equals y. Put it on the y-axis. Is that what we wanted? Okay, good so far. So now what? S sub g of what? If we want to a, comma, x. Now what's that telling? So, oh, jeez, what happened? Where am I? What the heck happened? Come back. Oh my God, are you kidding me? I'm trying. It only does one. All right, well, we're smart. We can do it. Equals integral a to y of square root 1 plus, in parentheses, total derivative of g of what? T d t d. Is it right now? Is that what we had? Squared. Thank you. How's it look? Stay right there. Okay, so here we go. So now we're graphing that. Again, we're putting values of arc length on the y-axis, and so it should be S sub g a comma y or x. So this is the line that's telling GC to graph it. So what we want to tell it is we want to say we want to take that quantity and put it on the horizontal axis. So it should be x. Okay? And then we want that from 1. What's going from 1 to 4? X. Okay, now if I graph that, it's going to graph it overlapping with my original graph of the function that we're measuring the arc length of, right? The g of y. So here's how you do it. Open the second pane. Have you guys done this before? You use apostrophe on every y and x. So any y apostrophe, x apostrophe, x apostrophe. Now this has nothing to do with the derivative. It's not prime. This is just the way GC will allow you to open a second window. Okay? So you got to make sure you're not seeing that as y prime, x prime, meaning derivative. It's not. It's just what GC has for if you want to graph two graphs side by side. So we'll make that red, say. Oh, I should have asked you to predict what that graph was going to look like. That was an important question. So, but oh well, there it is. So we make sense of this, right? Why does this make sense? Why does this graph make sense as the arc length of this, wait, as a function of y? Okay, so have a conversation about that. Why does this graph make sense if it's the arc length of this one as a function of y? This graph makes sense as the arc length of this with respect to y. So why? So first of all, why does it not start at the origin? Why does it start here at 1, 0? Right. So arc length is going to start accumulating at what y value? 1, right? So we don't get any accumulation of arc length until we start at 1. So our independent variable here is y, so it's going to start here at 1. And then what is this? So these values over here we think of as what? What do we think of as those values? Y values on this graph, right? Y going up. And so if I pick a point on here, oh my goodness. What's going on? Oh, I got the pen on there. All right, so here's a point. 3.23, 2.54. Or 2.55. So I want you to interpret the meaning of that point on this graph. What's the meaning of that point on this graph here? Go.
So when x on this this graph is 3.23.
3.23 or 2.55? 2.55 is the arc length. Which arc length is it? Is it an arc length on this right graph or the left graph? Left. So what arc length is 2.55? The whole thing? What's that? And what coordinate is 3.23? The x, up till x is 3.23? Y. So right, so from 1 to 3.23 on this curve, it tells us that point over there tells us what? What does this tell us? What is the length? This is 2.55 units long, the length of that arc, right? Starting from y equals 1 up to y equals 3.23, it's about 2.5 units long. That's what you should have said. Questions on that? Make sense? Any questions? Okay, let's move on. All right, so I want you to represent the total arc length of this, right? Symbolically represent the total arc length. So we should be that you shouldn't need to think too hard about. Let's see. Jessica, can you represent the total length of this arc symbolically? Like what symbols would you write to represent that length? How about in the most succinct way possible, the shortest way you can? Okay, what would it be? Yeah. Is it G of something? Trinity, what do you think? You trailed off there. S of G of? She wants S of G of 1 comma 4. Oh, she's changing her mind? So you still want S of G though? S of G of what? Johan, what do you think? Thinking 1 to 4. Some people are nodding. Let's just do that. What about it? What is this? Is this right? So this means that we're going to start at a equals 1 and we're going to integrate all the way or accumulate arc length all the way to 4. Is that the total length? So the total length of that arc is 3.3428. Okay? Where does this show up over here on this graph? So how can you relate this, what we just did, to this graph here? When x equals 4. So we're going to put x equals 4 in here. And we're going to get the function value. What would the function value be? There it is. See? So when we put in 4, meaning the y value over here is 4, this tells us the arc length up to 4, which is the whole arc length. And there it is, 4 comma 3.428. Okay, so that's the easier version of this. So then when we get into surface area and we change our coordinates y and x, it gets a little trickier. So that's why we had a warm up there. So now we're going to do surface area. Now I'm going to rotate this curve around the x-axis. This one here. So I'm going to take this one off, take this graph off. Any questions about the arc length? So let's take that off, and we're going to start again, and I'm going to rotate this curve, our ln of y, gy equals ln of y, around the x-axis. And I want you to find the rate of change of surface area, the rate of change of surface area function with y as the independent variable. So first of all, let's draw a picture here. So when I revolve this around the x-axis, and I'm thinking about the surface area that results, what kind of picture would I draw here? I'm going to rotate around the x-axis. Or what kind of geometrical object will I get when I rotate this about the x-axis, just thinking about the resulting surface area? Like a what? Like a funnel. See that? Right, so like this. So that's the, when I've gone halfway around with this thing. Hello. My hands up there. About halfway around, it'll look like that. And then we think about it's the best funnel I've drawn all day. So is that what you imagined? Okay, and so then what will our elements be? So there's when we do this, we think about in the current interval, we're accumulating surface area. In the current interval, we get a frustum, right? It's like a chopped off cone, or I like to call them ribbons, right? The ribbons. So can you imagine what one, like in the current interval? So we got some typical intervals, the current interval. What would one of those ribbons look like? Could you draw it, or at least imagine it? What would a ribbon look like here in the current interval? Would it be standing up vertically, or would it be laying out horizontally? The ribbon. Is it going to be like a vertical ring or a horizontal ring? First of all, sorry. Yeah. So is it going to wrap around vertically or horizontally? Vertically, right? And then we remember that in order to do surface area, you have to. It can't be a horizontal edge, right? It can't be like a right angled ribbon, but we have to use the arc length, right? We have to use the arc length so that our ribbons have the bevel on it, right? They're like. So one of those is going to look like this. That's not the best ribbon I've drawn all day, but you get the idea. Okay, so now this is the image that we have. We're going to accumulate through delta x intervals. We're going to accumulate surface area by watching these ribbons grow in the current interval, right? So I want you to define the rate of change of surface area with y as the independent variable. So even though, let's see. Yeah, so actually y is increasing through delta y intervals, but the ribbons still look like this. Okay, the ribbons still look like this. They're the ones that are rotated about the x. Can you imagine that? Yeah, so y is still increasing through delta y intervals, but the ribbons that we have look like that because we rotated around the x-axis to start. Okay, so go. So can you define the rate of change of surface area with respect to y? Go. Rate of change of surface area with respect to y. Surface area function. So we rotated about x, but I want to let y increase through delta y intervals and write the surface area function in terms of y. So So 2 pi times g of y, okay? Oh, sorry, yeah, right. Sorry. Okay, 2 pi g of y. Okay? Okay, so we're doing the rate of change, right? So will we have the dt in that? Yeah, so when we accumulate, then we do rate times change in independent, right? Like what dy equals mdx. So we're not accumulating, we're just writing the rate function. So it's just the m part, right? Dy equals mdx, so this is just the m part. Okay, and then what do we want to call that? This is the rate of change of capital S. So this is of g. That's what we're going to do. So the rate of change of surface area of the function g. Of what? Y. Okay, how do we do? Agree with that? Okay, so everyone agree with that? Yeah. Okay, so let's look at, so remember when we did our rate of change of these, using these ribbons, what did this was? 2 pi times, what is this? Radius. So look at the ribbon. What is the radius of the ribbon? Is it an x coordinate, y coordinate, big change in x, big change in y? What is that? That's just the y coordinate. See that? The radius of our ribbons, because we rotated about the x-axis, the radius of the ribbon is y. What is g of y? G of y is x. G of y is like how far we are over this way. So what should we put instead? Just y. Do you see it? Because the radius of our ribbon is the y coordinate of the point in the current interval. So it should not be g of y, but y. Now, when we're doing it as a function of y, so when we get to the derivative, this is fine. The derivative of g with respect to y. Okay, does this make sense? So the geometry matters. You have to have the right image of these to get this right. You can't just follow the formula, right? You have to have that image. Any questions on that? Does it make sense? See if that's what we put. R sub y, sg, 2 pi y. I think that's it. Okay, so that's our surface area. Where'd my graph go? My graph of the original function. All right, so now define the surface area function with y as the independent variable. Go. We want this surface area function. If that's the rate of change, what's the surface area function? Go. All right, I'm sorry, you went too fast for me. So SGY, a comma y. Good. Yep. What do you think? We got one thumbs up. Is that what he said? Very good. Okay. Moving on. Any questions on that? So this is the convenience of defining the rate function separately, is that we can use then the function notation in the accumulation function, and it makes it a lot cleaner, right? So, but we could have put this expression in, right? We could have put that expression in there with t's in it. And we have the same thing. All right, represent the total area of the whole surface, right? The whole funnel. Or like horn bell, like it's kind of like the bell of a horn. Represent the total area. Victoria, can you do it on the fly?
Probably not, but I'll
Give it a shot.
so it's going to be the S or G of 1, 2, 4.
4. What do you think? Is this it? Okay, and so that's 51. 51. What was the arc length? Was like 3, right? 3.2 or something like that. And the surface area is 51. Why is it so much of a bigger number? Yeah, you're taking that and you're rotating it about all the way around, and now you're measuring area, right, instead of just arc length. Okay. So again, it's this thing here. So we just got the surface area of that whole thing. All right, now I want to graph the surface area function of the right-hand pane, independent variable on the horizontal axis, surface area on the vertical axis. Go. See if you can write out. What should I type into GC so that over there, I get my independent variable horizontally, and then on the vertical axis tells me what the surface area would be. Go.
Just write it. Would it be like? Would it still be like this? The actual function is divided into y.
Okay, Eric. You, Eric? You're up. Tell me. So if I want to graph it, how do I set it up? How do I format this to tell GC to graph a function? So if you say x equals SG, then you're going to put values of surface area on the x-axis. Is that what you want? Where do we want values of surface area? On the vertical axis, right? So it's going to be y equals S sub G what's that? So is it y or x? So this is the graphing statement. So we were going to tell GC for this S function what to put on the horizontal axis and what to put on the vertical axis. So we want to put what? Y values in the function on the horizontal axis in the graph. So here I should put x, right? This is the graphing. It's telling GC, put on the x-axis whatever's here in the function, right? Put on the x-axis when you graph it, whatever's here in the function. And then put on the y-axis in the graph values of this. Is that what we want? And that's from? To 4, right? And then again, this is on the x-axis of our graph. But then to do the right-hand pane, we're going to use apostrophes. Okay, so before I graph it, sketch. What do you think it'll look like? You sketch what you think this function will look like before I turn on the graph. Oh, there it is. Blew it again. All right, what do we get for the total surface area? 51.1814. How does that relate to this graph? How does the total surface, where does the total surface area, how does it relate to this graph here? Allison, what do you think?
So when y is equal to 1, the original function, then that's where the surface area starts. It goes up to, what, 51.
Okay, so this right here, how does this right here relate to this graph? So x on this graph, you're saying?
Yes.
So right, so as
The y value is
values of y over here, right? So where should I put this point? No, to relate to this right here.
51.18.
Okay, so this graph now tells me that what? When y equals 4 on this graph, which we're showing on the horizontal axis, we get a total surface area of the whole funnel of 51.184. Okay, so now now I want to redefine the curve of g, so I'm going to start over again. Questions on this one? So now we're going to redefine the curve of g, so what do we have? Originally we had x equals g of y, as y is a function of x, and that was ln of y. So I want to write this as the same curve as y now is a function of x. How would I do it? That function will be named f. So what will y be as a function of f? Or sorry, as x, function of x? Y equals e to the x, right? It's like the inverse function, right? So x equals ln of y is the same as saying y equals e to the x, right? Those are inverse functions. So it's the same curve here. It's the same curve, but now I'm writing y as the more conventional way, right? Y is the dependent variable for x independent. Now I want to rotate, same funnel, rotate about the x-axis, define the rate of change of surface area with respect to x now. Rate of change of surface area with respect to x. Go. What's the rate of change of surface area with respect to x this time? So for the same funnel, for the same ribbons, but now that rate of change as a function of x rather than a function of y. So this is what we want now.
The radius would be outcomes. Oh, right. Oh, it was meant to be on. Yeah.
Let's see here. How about Sebastian? Did you figure it out? The rate of change of surface area. Now with respect to x, what would it be? What do you think? So now, again, the radius is this right here. The radius is x-coordinate or y-coordinate? Still the y-coordinate. It's the same ribbon, right? It's the same ribbon, but in terms of x, we need f of x, right? So, or you could have put, instead of f of x, you could have put what? E to the x. Yeah, so f of x or e to the x, either one. Okay, while I type that in, I want you to find the surface area function with x as the independent variable. Go. That's right. Okay, what's the surface area function? It's such a bummer. Didn't get to the best part. So what is the surface area function? Integral from a to x of. Okay, just you can pack up, but just don't walk away yet. R sub s f t. Is this right? All right, now I'm going to graph that. Don't have time.